Hi, my name is David Bang, and I would like to discuss the asymptotic shape of the concave majorant of a Levy process. This work has been done jointly with Jorge Gonzalez Cazares and Alexander Milatovic, both associated with the University of Warwick and the Alan Turing Institute. So, if we consider a sample path of a Levy process x on the interval 0t, we have here a continuous time stochastic process with independent and stationary increments. We'll see that it starts at 0 almost surely. It has some large jumps, and it will possibly have infinitely many small jumps, which we cannot see here in the picture. It will also possibly have a Gaussian component. So what we are interested in describing is the concave majorant of this Levy process. So a concave majorant is the smallest concave function that's always larger than the process itself, the path of the process. So this function, the concave majorant, will be piecewise linear. What this means is that it's infinitely many small piecewise linear segments, which we will call phases, that bound this function from above. So what we're interested in describing is the length of this concave majorant together with the supremum of the process, the time of the supremum, and the endpoint of the concave majorant. We're interested in finding the correct asymptotic mean for the length, and we're interested in describing limiting distributional theorems, where we also consider how the dependencies between the length, the supremum, the time of the supremum, and the endpoint. So if we first consider here the concave majorant in black, and we have the upper bound here being blue, which we will call the tent, we have that when upsilon t frown denotes the length of the concave majorant, we have a very simple lower bound if we just say that, okay, of course it's bounded by the length on 0t being capital T, and the upper bound by t plus 2 times the supremum minus the endpoint. This holds for all Levy processes. So if we assume a bit more, so we assume that it's zero mean and has a bit more than first moment, then the upper bound will converge to 1 almost surely. So we have a rough idea of what size the asymptotic mean will be, which will be around capital T. So this gives us now an idea of where to look, and this leads us to the main aims of this presentation, which is that we will describe the fluctuations around the asymptotic mean of the length of the concave majorant, and we'll describe these distributional limit theorems for the centered statistics and the limiting dependence between the centered length and the supremum, the endpoint, and the time of the supremum. So if we first consider the case of finite second moment, so we have zero mean, we have a positive finite variance, and we have a Levy measure nu. And then for time horizon capital T, we define theta t to be this deterministic function x squared log plus of minimum between t and x squared nu dx, which is a part of the centering. So the centering for the length will be capital T sigma squared over 2 ht and theta t, where ht will be the number of maximal phases that have length larger than 1. So a phase is maximal if it contains all the phases of the same slope. What's nice about ht is that it has its own CLT, so it has a centering log t and the same scaling as the centered length being square root of log t. We have as well the triplet here for the supremum, the endpoint, and the time of the supremum. Now we have that this converges jointly in distribution to this vector here, where Z1 and Z2 are standard normal random variables that are independent, and they are independent of the Brownian motion B, where we have the supremum of the Brownian motion, the endpoint, and the time at which the supremum is attained for the Brownian motion. What's really nice here is that we see that these are independent. So the two standard normal random variables are independent of the Brownian part. So what this means is that we in the limit see independence between what has to do with the length and what has to do with the supremum endpoint and time of the supremum, which is really nice. And how does this arise? This comes from the fact that all the phases with a length smaller than 1 will not contribute to the fluctuations of the length and ht. However, all the phases of the concave majorant of moderate size will contribute in aggregate to the fluctuations. But if you take any finite set of fluctuations of moderate size, this will not survive in the limit fluctuations. And this is a really important fact, because when we consider the last triplet here, these behave such that it's only the largest few phases that influence the scaling limit. And hence we see this independence in the limit, which is very strong. So directly from this theorem is this nice corollary where we have a deterministic centering. So if we just consider the first two instances from before, instead of ht, we can then substitute in log t, and we still have this theta t, and this will converge to a normal distribution with a bigger variance before, because we're penalized by the fact that we have a deterministic centering. Theta t will be little o of log t, and again, z is just a standard normal random variable. If we now assume just a bit more than second moment, so we assume that the integral x squared log plus of norm x square root nu dx is finite, then the deterministic function theta t will be little o of square root log t, and thus we won't see this theta t in the limit. So we'll just have this very nice central limit theorem where the centering is very simple, being t sigma squared over 2 times log t. So what happens now in the domain of attraction? So we say that the Levy process is in the domain of attraction of an alpha stable law for alpha between 0 and 2 if there exists some positive function at and a alpha stable process as alpha such that xt over at converges in distribution to as alpha at time 1. At will be a regular varying function with index alpha between 0 and 2 without 1. So therefore we'll have that at will have the form t to the power 1 over alpha times a slowly varying function L. Another object that will arise as a limiting object will be the stick-breaking process. So we say that Ln is a uniform stick-breaking process on 0, 1 with stick remainders capital Ln given by some uniform IID sequence Vn if the following holds. So we take the stick of length 1, 0, 1, then you take a uniform random variable on this stick, so we call it 1. So we now have the stick fixed to the right. We break that off and we have something left. We now take a uniform random variable on what's left. We fix that uniform random variable. We break the part off we see here. Right, this was L2 and we break that part off. And then we have the new part where we take a uniform random variable and so on. So how does this object arise in the limit? So this comes as you see here. So let x be in the domain of attraction of an alpha stable law for alpha between 1 and 2 and have 0 mean. Then we see that the centering for the length is much simpler now. It's just capital T. The scaling is a lot different. Now it's at squared over t. The scaling for the supremum and the endpoint is at, and the scaling for the time of the supremum is t. This converges jointly in distribution to the vector we see here, where the last three instances have a very nice interpretation. So let's first see what objects we have in the limit. So we have the uniform stick-breaking process, Ln. We have a sequence of independent copies of the stable process at time 1, and we have that the stick-breaking and the sequence of independent copies are independent. So the last triplet here can be interpreted as being the time at which the stable process attains its supremum, the endpoint of the stable process, and the supremum of the stable process. So the first entrance do not have this same nice interpretation through a simple function of the path of the stable process. We do, however, know the tail asymptotics for the first entrance, and it turns out that this will asymptotically have the same tail as the squared stable process as alpha. So the reason why we have this infinite sum over these ln's is because that when we have alpha between 1 and 2, all the phases from the concave majorant survive. We don't have the same behavior as when we had finite second moment. So when we now consider instead alpha between 0 and 1, we have a very strong result. So if we consider again everything that has to do with the concave majorant and similarly everything that has to do with the convex minorant, then we have jointly for this a weak convergence to this very large vector, including all the information about the statistics. And again, these have very nice interpretations of being the supremum of the stable process, the endpoint, the time of the supremum, and 2 times the supremum minus the endpoint. And similarly for the convex minorant. What's really nice here is that we also know now the CLT for the entire convex hull, not just the concave majorant. So this is the strongest result, but it's also the easiest result to prove because this has very thin and very tall concave majorant, because it has some very huge jumps that will dominate everything. So we don't even need a centering. This will just hold directly. So what we also talk about in this paper is the tens and the hot. So if we consider the red process here, which starts at 0, goes to the supremum, and then goes to the endpoint. And this will be called the hot, and the tent will be as the upper bound, as we saw from a few slides ago, going to the supremum and then jumping down to the endpoint again. For these, we also construct distribution limit theorems, refine the centering, and refine the scalings. I want to mention here that the scalings are very different in the different settings, and also differs from each other. So if you consider the scalings of the process itself, we of course for alpha equal 2 have square root t being the normal central limit theorem for the Levy process. When alpha is between 1 and 2 and 0 and 1, we have the scaling being at such that it converges to the stable law. However, after centering, the scalings for the length of the hot and length of the tent will be very different. Say we look in the case of alpha equal 2, we see that the scaling for the length of the hot is 1. We don't even need to scale, whereas the scaling for the concave majorant is of course square root log t, and the scaling for the tent will be square root t. If we jump to the case of alpha between 1 and 2, we see that the scalings will be the same for the hot and the concave majorant, where it will be slightly different for the tent case. And then we jump to the strongest case of alpha between 0 and 1, and here they all agree, it's all the same scaling. So the main idea behind the proofs of these theorems is really the characterization of the concave majorant through a stick-breaking process, an independent stick-breaking process, and the increments of the Levy process at the time of the stick remainders. So this can be expressed like so. We have that the length of the concave majorant can be expressed by taking the square root of a stick breaking on 0t squared plus, here we have the increment over the stick remainders, which is a really nice object to work with and much easier than just working directly on the concave majorant. Similarly, you have also expressions through the stick and the increments for these last 4 entrances, being the time of the supremum, the endpoint, and this ht prime, which is a random variable closely related to the number of maximal phases with size larger than or equal to 1, expressed more thoroughly in the paper. Again, we have here that L will be independent of the Levy process. Another really crucial result that we had to prove for this paper was this result where we have a zero mean finite second moment Levy process. You define sigma t to be sigma minus the second moment of a truncated Levy measure. You have kt to be the Kolmogorov distance between xt over root t and normal random variable. And then we have a very nice result. So for a second moment Levy process, we know that the Kolmogorov, we have a normal CLT, and therefore we have that the Kolmogorov distance will converge to 0. However, we need some more regularity on the Kolmogorov distance. We need to know more. So in our case, we wanted to use it in a dominated convergence argument. So therefore, we wanted to know that this integral over 1 to infinity of the distance divided by t dt being finite, which is a very nice result. And it was very crucial for the proof of theorem 1, the first theorem for the case of finite second moment. So here are the references that I just mentioned before, and the arXiv link to this paper will be in the description of the video. And thank you so much for watching.